Hi. So today I have a very interesting problem to discuss. In fact, it's a question that many of us might have thought when we learned the Pythagoras theorem back in school. That is, if we are given three side lengths of a triangle, let's say that the three side lengths are A, B, and C, can we determine what kind of triangle will it be? That is, will it be an isosceles triangle? Will it be an acute angle triangle? Will it be an obtuse angle triangle? Or will it be a right angle triangle? So we know how to check if a triangle is a right angle triangle or not. We take the squares of the smaller two sides and add them, and if it is equal to the square of the longest side, then that with those side lengths we can construct a right angle triangle. But can we determine if the triangle will be an obtuse or an acute angle triangle? So we know that if we add the squares of the two smaller sides and we compare it with the longest side, square of the longest side, considering here in this case C is the longest side, then either a square plus b square can be greater than c square, or a square plus b square will be less than c square. So can we looking at these two cases, can we determine whether it's an acute angle triangle or an obtuse angle triangle? So this is what we are going to explore and discuss. So first let us construct an acute angled triangle. So what is given is triangle ABC is an acute angled triangle, and since it's an acute angle triangle, any altitude will lie inside the triangle. So I'm constructing an altitude AD where AD lies inside the triangle, obviously, because it's an acute angle triangle. Now if we assume that AC is the longest side, then what we are trying to prove is that, or what we are trying to find out is AB square plus BC square. We are trying to compare it with AC square. Yeah. So since no side lengths are given, this is a kind of generalization that we can do. So AB square, we can write AB square as AD square plus BD square, because triangle ABD is a right angle triangle and AB is the hypotenuse. So AB square can be written as AD square plus BD square, and BC square can be written as BD plus DC, the whole square. Yeah. And AC square, we can write AC square as AD square plus DC square. So on the left side we have AD square plus BD square plus, when we open this parenthesis, we'll have BD square plus DC square plus 2 times BD DC, 2 times BD times DC. That's going to be on the left side, and on the right side we have AD square plus DC square. So as we can clearly see that on the left side we have AD square. So let me just use a different color, AD square on the left side, and on the right side also we have AD square, we have DC square on both sides, and we have a lot of other things on the left side. So which makes it very clear that the left side is greater than the right side, which means AB square plus BC square is greater than AC square. So since this is greater, we can say that A square plus B square is greater than C square. That is, sum of the squares of two smaller sides is greater than the square of the third side. So when is this happening? This is happening in the case of an acute angled triangle. So this is an acute angled triangle. And similarly, if we consider an obtuse angled triangle, if we take an obtuse angled triangle, triangle ABC with an obtuse angle at B, and then we construct an altitude to side BC, obviously it will lie outside the triangle because it's an obtuse angle triangle and angle B is an obtuse angle. So if we try to find out, or if we try to compare AB square plus BC square along with AC square, now we know that the side opposite to the obtuse angle will be the greatest side. So the greatest side is AC. So we are again adding the sum of squares of two smaller sides and comparing it with the third side. So AB square, we can write AB square as AD square plus BD square, and BC square we can write as let's say just BC square, and AC square we can write as AD square plus DC square. And further we can expand DC as DB plus BC the whole square, and along with that we have AD square. So when we open this parenthesis, on the right side we have AD square plus BD square plus BC square plus 2 times BD times BC, and on the left side we have just AD square plus BD square plus BC square. So we have AD square plus BD square plus BC square on both sides, and on the right side we have something extra, which means that the right side is obviously greater than the left side. That means AC square is greater than AB square plus BC square. So this is happening in the case of an obtuse angle triangle. So we have generalized the case of an obtuse angle triangle as well. Now this is a very useful piece of information. Let me just show you a couple of questions where it can be used. So here we have 2 questions. In fact, these are questions taken from a very old text called Leelavati, written by an ancient Indian mathematician Bhaskaracharya in 1150 CE. So the question is like this: we have a triangle and the side lengths are given as 13, 14 and 15. AD is the altitude to BC. We need to find the lengths of AD, BD and CD. So generally when we try to solve such problems, most of us are habituated to draw an acute angled triangle. But how do we know that it will be an acute angle triangle? So we need to be first certain, because if we are not certain, or if we draw an acute angle triangle instead of an obtuse angle triangle, which is the case with the next question, that is 10, 9 and 17, the side lengths are changing. Now if you look at this, 10 square plus 9 square is 100 plus 81, which is 181, and 17 square is 289. So 181 is less than 289. That means in the second case it will be an obtuse angled triangle. And if somebody tries to solve it using by drawing an acute angle triangle, then they will get this, that is B, D, C and A, that is BD, they will get as a negative number in the second case. So for solving such questions, we need to really know whether it's going to be an acute angle triangle or an obtuse angle triangle. So this is a very useful information, I feel, and it is not much discussed in not just not much, it is not discussed in school curriculum, that is these two properties, but if we know it, it's going to be very useful in some problems in triangles. And in case somebody is getting confused that in which case will it be greater than and in which case it will be less than, all we can do is we can just keep the example of an equilateral triangle in mind. And equilateral triangle is an acute angle triangle, and in an equilateral triangle all 3 sides are equal, and we know that a square plus a square, that is the sum of squares of 2 sides, is greater than the square of the third side. So this is always true, and this is happening in the case of an equilateral triangle, and in equilateral triangle is an acute angle triangle. So if this is happening in an equilateral triangle, then that is what is going to happen in an acute angle triangle, and from that we can know that a square plus b square is greater than c square in an acute angle triangle, and it will be the other way around for an obtuse angle triangle. So I hope this was useful for you.